Good afternoon, everybody, and it's my pleasure to welcome you to the first colloquium of this academic year. And on behalf of the colloquia committee, I'm very happy about telling you that we have a great program. We work very hard to produce it over the summer, but if you go on the website, you can find the schedule until the very end of the academic year. And there will be, as usual, one colloquium for each month. So I'm very happy about that, and it's my honor to introduce today's speaker for the first colloquium of the academic year, Professor Hitoshi Murayama. Professor Murayama got his education at the University of Tokyo, where he got the PhD in physics. Then he was a postdoctoral fellow at the Lawrence Berkeley National Lab, and then he joined the faculty at the University of California in Berkeley, where he has been ever since. Meanwhile, he was the founding director of the Kavli IPMU at the University of Tokyo, I believe until 2018, since the foundation until 2018. And the research activity of Professor Murayama is remarkably broad. He's a theoretical particle physicist with interest in physics beyond the standard model, as broadly defined as you could imagine. And in particular, he gave contribution on models for physics beyond the standard model, dark matter, dark energy, inflation, grand unification, neutrino physics, and even condensed matter. Just to say a few words about today's speaker, recently he served as a chair for the P5 panel. It was a panel that was supposed to shape the priorities for the future in particle physics in the United States for the next few decades. And the list of achievements is, of course, long and impressive. I will give just a few examples. He was elected fellow of the American Physical Society, of the American Academy of Arts and Science, and as a member of the Camlan collaboration, he shared the Breakthrough Prize in Fundamental Physics in the year 2016. The subject of today's colloquium is a very fascinating topic. The title is When a Symmetry Breaks. And Professor Murayama will tell us about the concept of spontaneous symmetry breaking, which unifies a lot of physical systems, from something we're very familiar with in our everyday life, like a magnet, like an ice cube, to more, let's say, to less familiar systems such as superconductors or even the Higgs field. And we will hear a lot about this, and in particular, we will hear about the very first work by Nambu, Goldstone, Anderson, and Higgs, and we will see that they can be extended. They can be extended to describe physical systems that we encounter in the experiments. So it is really a pleasure to introduce you. I'm looking forward to your colloquium, and I would like to thank you for being here. Let's welcome Professor Murayama.
Thank you. Thank you. Thank you. And thank you, Francesco, for a very generous introduction. And as I actually listen to a longer and longer introduction as time goes on, I always start feeling old. But anyway, so thank you, Francesco, anyway. So as Francesco already pointed out, the title of my talk today is When a Symmetry Break. But just before getting into the talk, I've been in Padova several times in the past. And one last time I remember very well was when I was actually producing a TV show, working with the broadcaster named NHK in Japan, which is sort of similar to BBC in the UK. And I had a pleasure of visiting the place where Galileo lived, where he used his telescope for the first time. And then I moved to Florence to visit a library where I could hold his handwritten manuscript in my own hand. So that was really, really special moment. So I had a great connection to Galileo. And so when I became the founding director of this Kavli Institute that Francesco mentioned, we actually created a pillar in this interaction area, which we call obelisk. And on that obelisk, there's an inscription, L'universo è scritto in lingua matematica. So this was an institute that unifies physics and mathematics into a single institute. So anyway, so that's a little introduction between my connection to Galileo, I guess. So my talk today is talk about something that is common to magnets on your fridge, cubes of ice, halibut, and rack of laundry. So I always ask the quiz, so what's common between them? But Francesco already gave you the answer. So there's a concept called spontaneous symmetry breaking, which actually unifies all of these different phenomena. So before getting to symmetry breaking, let's talk about symmetry. And as everybody here knows, symmetry is a very fundamental concept in physics, and that goes all the way back to a famous theorem by M.E. Naylor, who pointed out that if you have a system with a symmetry, that would always lead to a conservation law. And the conserved quantity ends up actually generating a symmetry, so they go really hands in hands together. So an example of a symmetry, for example, is that if you look at a picture of a beautiful galaxy like this one, you are also bound to find a galaxy that has the spirals in the opposite orientation, and that's because laws of physics seems to be invariant under taking the mirror image from the original one. There's a little violation of that called weak interaction we get to in a moment, but by and large, laws of physics is invariant. You don't distinguish left from right. And also, you're bound to find galaxies or all different orientations, and that demonstrates that the laws of physics is symmetric under rotation of the systems. And that leads to the conservation of angular momentum. And if you look at the distribution of galaxies in the universe, and this is actually based on real data taken by a project called Sloan's the Sky Survey, by and large, anywhere you go, universe looks pretty much the same. There are some dense spots, some empty spots, but by and large, everything seems to be the same, no matter how far you go. And of course, if we really try to do this kind of space trip, you have to travel at a speed at 100 trillion times faster than the speed of light. So don't try this at home. But the point here is that the laws of physics seem to be translationally invariant, and that's a symmetry that leads to the conservation of momentum. So that's something we see in Newton's equation. If you do the left-right, the flipping, called parity, you put -1 of the axis, you can do a rotation, you can do a translation, and laws of physics like F equals ma doesn't change under these symmetry transformations. So that's a symmetry. But if you look around, like yourself, most of us are right-handed, and vast majority of us have our heart on the left-hand side of the body. So that actually points to a question. So if the laws of physics have high degrees of symmetries, what is the origin of diversity? That's the question. And part of the answer to this question is this idea of spontaneous symmetry breaking. So for me, sort of kind of hero who came with this concept is Yoichiro Nambu, who passed away already, but was a Nobel laureate. And so he came up with this following idea. Suppose you have a system which has some degree of symmetry, which we call G. But suppose its ground state of that system respects only part of that symmetry, which we call H. Then there are multiple ground states which have exactly the same energies, and they correspond to coordinate of space called G mod H. So that sounds a little technical. But the simplest example I can come up with is the rack of laundry. So I do laundry, and I hang the shirts to let it dry without doing a dryer to save carbon dioxide production. And when I hang the first shirt, it doesn't matter if I hang it facing left or right. But when I come with the second shirt, I have the tendency that I want to hang the second shirt facing the same way as the first shirt. And if I keep doing that, at the end of the day, I get surprised, oh my goodness, why is everything facing left? And of course, it really doesn't matter if all of them facing left or all of them facing right. It could have been either way because of the symmetry between left and right, but end result of the rack of laundry has spontaneously broken the symmetry between left and right. You end up finding a ground state where all the shirts are facing left. You could have chosen another ground state where all the shirts are facing right. It could have been either way, but you have to choose one between them. So that is the spontaneous breaking of symmetry. And we see many examples of this kind. For example, this is halibut. And this is one of the flatfish where two eyes are on the same side of the body. And clearly, this kind of fish has evolved in a way of hiding in the ocean floor in the sand to protect themselves from predators. So there's an obvious reason why they have to do that. But they had to decide to put two eyes on the left-hand side of the body or right-hand side of the body. They could have done it either way. And as a matter of fact, another kind of the flatfish called flounder, has 2 eyes on the right-hand side of the body. And I happen to know that they are different species because I eat both of them. They taste differently. Halibut has such a clean taste. It's great for sushi. Flounder has a little bit of an earthy odor, but it's actually also very delicious if you actually simmer in sauce for a while. But they do taste differently. They're different species of fish. So each species of fish ended up choosing one way or the other to put their eyes on one side of the body. And there's a famous biologist named Reiko Kuroda in Japan, and she actually studied conch. This is kind of shellfish that winds around, but as you can see, winds around in one particular direction. And when conch starts with a fertilized egg, the cells start to divide, and when it gets to about 8 cells, they do start to wind around. So the experiment that she did is something a little brutal. So when the cells start to wind, she actually nudged the cells and forced them to wind in the opposite direction. And the conch is such a simple biological system, so after being forced to wind in the opposite direction, they ended up becoming a full-grown conch without any problems. But of course, which way they wind is written into DNA. So even if you take these wrong orientation of conch, their children would wind in the usual way. So it's written into the DNA, so you can change that. But what it demonstrates is, once again, it really doesn't matter. Conch could have done it either way. It just happened to choose one way over the other. And we see examples also in chemistry. So if you take sugar, sugar has a chemical formula like this, and in the case of glucose, they have 2 different orientations too, left and right. And it turns out that D-glucose is a sugar we consume in cakes and snacks and so on. L-glucose is not something you eat. Even if you do eat it, you can't actually digest it because you don't have the enzyme to break down L-glucose. You can break down only D-glucose. And this is actually a great moment to think about businesses because if you happen to come up with an inexpensive manufacturing process to produce huge amount of L-glucose, you can be an instant trillionaire because they have exactly the same chemical composition, completely safe for your body. It tastes about the same, sweet, but it's 0 calories because you can't break it down in your body. So now you see how you can make money, right? But remember, you heard it from me if you start a business like that one. So there's a clear distinction between left and right here. So it turns out that entire biomass on a planet can produce only D-glucose, that's what plants do, and consume D-glucose, that's what we eat. And so if you go to a different planet, maybe they live on L-glucose instead of D-glucose, but nonetheless, each planet in each biological system chooses one orientation over the other. The same is true is also with amino acids or the proteins are made of. So recently, there was actually a space probe that went to an asteroid named Ryugu, done by the Japanese Space Agency. And this, the space probe went there, took the sand sample, and came back to a planet and left the sand sample with us. And when people analyzed what's in the sand in this asteroid, people actually did find amino acid in them. And that's interesting because there has been this the lingering theory that maybe life on Earth came on asteroid to start with. So I wonder, well, maybe this kind of asteroid does have life on it. But when they studied it, it turned out that they found the 50-50 composition of left-handed and right-handed amino acid, while our entire system of biological system on a planet is based on one type, not the other one. So having found 50-50 orientation of amino acid can be taken as a good evidence that it's actually not a life system on this asteroid. So you learn something by looking at a simple distinction between left and right. And you can imagine that all of these examples can be expressed in a simple equation, v going to x squared minus 1 whole thing squared. So x going to minus x is the left-right flipping. I call this parity. And this potential energy doesn't change when you change the sign of x. So it's left-right invariant. That's a symmetry. But when you randomly throw balls into this potential, sometimes it bounces around and falls into this minimum, sometimes it bounces around and falls into that minimum. But either way, it chooses one of the minima, not both of them at the same time. So that is spontaneous symmetry breaking. Even though the system has this perfect symmetry between left and right, once you find the minimum of the potential, you choose this one among the two that could possibly be there, and then you say symmetry is spontaneously broken. So that's an example of what we call discrete symmetry, because you can change left and right by one, twice, but you cannot change them continuously from each other. But there are examples of symmetries where you can do a continuous change. And this is actually an example I took from a write-up by Nobel Foundation when Nambu received Nobel Prize for this concept. So they talked about this pencil standing upside down. That doesn't sound possible. But if you believe in Newton's equation, and if you manage to perfectly let it stand upside down, and if there's no wind or any other perturbation of the system, then it should stay standing up, because there's nothing that would distinguish this direction, that direction, that direction. But of course, we know just by a little breath, the pencil would fall down in one of these possible directions. And you can't predict which way that might be. It can fall into any directions, but at least chooses one direction among all the continuous possibilities of 180 degrees direction where pencil might fall to. And this write-up also uses another example of the standing rod. And if you press the rod from the top with a not a strong enough force, then the rod stays standing straight up. But once you get to some threshold of the strong force to push it down, at some point the rod would buckle. And once again, it can buckle this way, or that way. You don't know which way, because it can go in any direction. But when the rod buckles, it has to choose one possible direction out of 180 degrees. So once again, we say that symmetry of rotation around this axis had been spontaneously broken. And that's what you see in magnets on your fridge. So the magnet is made of a bunch of small magnets of individual electrons. So each electron has a magnetic moment, so it's a little magnet. And when you have the high temperature, that each of these spins are randomly oriented, so you don't have any particular direction. But when you cool down the system, then the spins start to line up in the same direction. They may line up this way, they may line up that way, but either way, they do line up. And when they do line up, they have to choose one direction over the other. So in this case, spins can orient into any possible direction in 3 dimensions, but it has to choose one particular orientation when you cool down the system, and therefore, rotational invariance is spontaneously broken. And that happens also when you freeze stuff. So I'm not talking about frozen like this one, but I'm talking about frozen ice. So if you start at a high temperature, then water, of course, is in a vapor, it's gas. And in the form of gas, each water molecules are moving in random directions. So there is no particular position, there is no particular orientation to the gas of water molecules. But when you freeze water into cubes of ice, then they line up neatly to form a crystal. So they have a particular orientation and occupies a particular position. So in this case, what happened is that translational symmetry is spontaneously broken because crystal occupies a particular spot. And rotational symmetry is also spontaneously broken because the crystal points in one particular orientation. So in this case, many different, the continuous symmetries are spontaneously broken. And at cold temperatures, many interesting things do happen. For example, when you cool the liquid of helium-4 into a very low temperature, it is known to become a superfluid. So inside this beaker, they put helium in there, but once it actually goes below the critical temperature to become a superfluid, it loses viscosity that you can see is dripping from the bottom of the beaker, which has tiny, tiny holes in them. And that's because there's no viscosity for the flow of the helium. And that happens when a wave function of the helium atoms in a macroscopic way has a symmetry of changing its phase, because wave function absolute squared gives you probability, so changing phase doesn't seem to do anything about it. But that symmetry is spontaneously broken that leads to this amazing phenomena of losing viscosity. And if you actually also have electricity on top of that, then you're talking about superconductor. The electrical current flows without any resistivity. And that's what you typically do in undergraduate physics experiment, namely that you cool a piece of metal to a low temperature so that it becomes a superconductor. Then it can float on a piece of permanent magnet, and that's an Meissner effect. And magnetic fluxes are pinned inside this piece of superconductor. That is also a manifestation of spontaneous symmetry breaking, of the symmetry to change the phase of the wave function. And this is actually becoming really a industry application, because especially in Japan, we are now building magnetic levitation train, maglev, which floats so that it can go at a speed like 600 kilometers per hour without much of a shaking, because it's floating in the air. And the way this entire train gets float is because of this superconductivity. And this may be the first industry application of high temperature superconductivity in the world. So this is actually a useful stuff. So the only difference from the previous case of this discrete symmetry to go to a continuous symmetry is that you take this potential, grab it at the center, and rotate it around so that potential now looks like this. And this potential can be written with this equation. So x and y can rotate among each other. X plus y squared is constant when you rotate. And this potential, therefore, has a rotational invariance rotating around the axis. But once again, when you randomly throw in balls into this potential, it bounces around and eventually finds a minimum here, or maybe there, or maybe over here. But it has to choose one particular angle among all possible angles of 180 degrees rotation. So that is the spontaneous symmetry breaking of a continuous symmetry. In the case of particle physics, that was actually very important when we studied the nature of a force called weak interaction. So weak interaction is the force responsible for things like nuclear beta decays. Neutron can decay into proton by emitting an electron and anti-neutrino. So weak interaction is responsible for that to happen. And try to understand what exactly this force is. So people built big accelerator at CERN in Switzerland and French border called LEP, Large Electron Positron Collider. And using this machine, they could actually produce a large amount of force carriers for this weak interaction and could study the nature of this force in great detail. And then we discovered that weak interaction is basically the same kind as the electromagnetism. So that's great. That sounds very familiar to us, except for one big difference. The weak interaction goes only over a distance of 10 to the minus 16 centimeters. That's 1,000 times smaller than the atomic nuclei. It's an incredibly short distance. That's only how much weak interaction can go. But we also know the electromagnetism is a long-range force, because if you hold a compass in your hand, the needle of your compass gets pulled by the North Pole of a planet. It goes over many thousands of kilometers. It's a long-range force. So if these two are of the same kind, how come that one of them is long-range, the other one is incredibly short-range? That was a major puzzle for many decades. And that actually is the place where we had to learn from our friends working on condensed matter physics. So I already told you that piece of superconductor can float on a permanent magnet. And that's because the magnetic field gets pinned into a thin flux tubes inside a piece of superconductor. And the fact that they are pinned in this narrow tube means that the magnetic field has become a short-range force inside a piece of superconductor. It goes over like several microns. It doesn't go very far. even though the magnetic field outside the superconductor is a long-range force, as I talked about for the compass needle, inside the superconductor, it has become a short-range force. So then people said, aha, this is the universe we live in. We are living in a cosmic superconductor where something is forcing this weak force to be squeezed down to a very short range. So what is actually causing it? So in the case of superconductor, we know the answer because you can turn off the cryostat, let it heat up, and see what's in there, and you see electrons. So in the case of superconductor, electrons pair up into something called Cooper pairs. They end up occupying this superconductivity as a condensate in it, and that is actually making the magnetic force become short-ranged. So in the same way, we think our universe has something filling it up to form a condensate of some kind, and that something is what people call the Higgs boson. And because we are living in a universe filled with the frozen Higgs boson, when the weak interaction wants to act on some other body, it gets bounced around and doesn't really go very far. That's why it has become short-ranged. Even electrons in your body, they actually want to go with speed of light, but they do bounce around because of this frozen Higgs boson in the universe a little bit, not as much as a weak boson, but a little bit. And that's why electrons get slowed down, and they can happily move about inside atoms in your body. But the photon does keep going with speed of light because it's a particle of light. And the reason being that Higgs boson doesn't have any electric charge. Photon, or electromagnetism, happens on something that has electric charge, but because Higgs boson doesn't have electric charge, photon doesn't realize it is moving in the ocean of the Higgs boson, so it just keeps moving with speed of light. So that's what's happening in the universe as we speak. And we also need the Higgs boson to be there with exactly just right amount. If we have too many of them, weak force really doesn't go anywhere. Then it turns out the sun doesn't burn, and we can't live in that kind of universe. If the Higgs boson were too few, then weak force can go over a long distance. Then the whole universe becomes radioactive, and we probably can't live in that kind of universe either. So we need to have just the right amount of the Higgs boson frozen in empty space today so that you could happily live. Namely that if the Higgs boson universe for some reason evaporates at this instant, then all of the atoms in your body would have electrons, and electrons start moving at the speed of light, so atoms would disappear in an instant. And you may wonder how old I am to have a picture with Einstein shaking hands, even in full color, so don't ask me the question. But the point here is that both of our bodies would also disappear in a nanosecond if that happens. So Higgs boson in the universe is really keeping us in one piece. So they're really swarm of superheroes for us. But we still don't know why is this particle frozen in the universe today? What exactly is it? Where does it come from? So we are still trying to understand many of these questions about this particle that was discovered about 10 years ago. And for particle physicists, discovering a new particle takes a huge amount of effort. Many decades to build a machine, many billions of dollars to spend on running it. For condensed matter physicists, I'm so jealous that they can create a Higgs boson in their laboratory. So this, the professor Ryo Shimano at the University of Tokyo experiments with superconductivity I talked about earlier, which has this kind of potential I mentioned also earlier. So the superconductor is sitting at the bottom of this potential somewhere around this ring. So what he did is to smash a piece of superconductor with a femtosecond pulse of terahertz laser. So basically, you whack the system by hitting it. And then, by hitting it, what used to sit at this bottom gets brought up in an instant, and then starts to go down, quick, 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 then it starts to go back and forth, and that leads to this electromagnetic radiation he could observe. So the frequency here is the mass of the Higgs boson. And he probably needed only like a $2 million to set this experiment up, so I'm very jealous of that. But you can see exactly the same thing can happen in our universe with the Large Hadron Collider. You whack the vacuum to bring the Higgs boson up and let it decay in your experiment, or do the same thing, you whack the superconductor and you can produce a Higgs boson in the laboratory. So all of these things have basically the same mechanism. And all of them boils down to a famous theorem called the Goldstone theorem, which you can find in any textbooks on quantum field theory. So what he said is the following: when a continuous symmetry is spontaneously broken, there appear the same number of massless particles or gapless excitations as the number of broken symmetries. And I tell you more about what it means in a moment. So point here is the same number of massless particles and broken symmetries. Another prediction he had is that when you actually create these degrees of freedoms, their dispersion relation or relationship between energy and momentum is linear. They are proportional to each other. That's the theorem. And that can be called Nambu-Goldstone's theorem. And we see manifestation of this phenomenon, again, in many, many different systems. For example, at the Large Hadron Collider at CERN, not only that they smash protons on protons, but they also smash lead nucleus on lead nucleus, called heavy ion collision. And when they do that, even one collision will produce this many particles. So what's going on here is that when you collide the lead nucleus on lead nucleus, it becomes so hot and dense, the protons and neutrons would melt into a soup of quarks and gluons it's made of. And that soup starts to expand like the Big Bang. And as it expands, it cools down and eventually forms all kinds of different particles. And most of them are called particle pion. And what you see here is the spray of pions coming out of this collision. And that is because this pion is a particularly light particle because it's meant to be one of those Goldstone bosons. And it's so light compared to all the other particles we know made of quarks and gluons. So you can see the proton and neutrons up there, pion is down here. It's very light compared to it, even though it's made of the same thing. And it's actually important that this particle is so light because this pion is what actually binds protons and neutrons together inside atomic nuclei in your body. If it's too heavy, it doesn't go very far, so it cannot bind the protons and neutrons because it can act on even neighboring proton. But because it's light enough, it can act on the neighboring proton and neutron so that it can bind them together into atomic nuclei so that your body stays in one piece. So if the pion weren't this light, then all of the nuclei you see in the periodic chart would fall apart, and you will be living in a very boring universe that has only one chemical element, hydrogen. So we really need to understand why this particle is so light. And that's actually very difficult to do because you're talking about this strongly interacting system of quarks and gluons. Recently, I've been working on trying to actually work that out. Again, learning from atomic physics this time. And in atomic physics, there is a phenomenon called BCS-BEC crossover. So BCS is the weakly coupled system of a bunch of fermionic atoms, and they can form a condensate like in superconductivity. But once you make this attractive interaction stronger and stronger, at some point, these fermions would form bound states to become a boson, and they can undergo Bose-Einstein condensate. And there doesn't seem to be any phase transition between these two limits. So what I'm trying to do right now is to, by taking a new strong interaction physics together with additional symmetry called supersymmetry, and if you break it a little bit, it is sort of like the BCS state where you can work everything out. But if you jack up the forces, then eventually you can't calculate anymore. But if there's no phase transition between these two limits, you will learn something about what's going on here in the real world of strong interaction by studying this hypothetical system with a higher degree of symmetry. Then I could really demonstrate that this system can break the symmetry called chiral symmetry so that the pions do come out light. So I'm learning a lot by actually doing that. So that's a typical thing theoretical physicists like myself do. When you have a problem which is very difficult to solve, like a real cow, I have to simplify it to make it into a spherical cow. And spherical cow doesn't look like the real world at all, but if you deform it just a tiny bit, you can start picking up all the features of the real cow from the calculable limit where I can handle theoretically. So that's exactly what I've been doing. But back to the subject of this spontaneous symmetry breaking, I mentioned this Goldstone theorem. And there are many, many cases you can see the Goldstone theorem at work. I mentioned a crystal, which breaks translational invariance. I couldn't draw three-dimensional crystal, so here I'm drawing two-dimensional crystal. And here's a 2D crystal. I have two examples of them. And what these crystals have done is to break symmetries of translation in this direction and also translation in that direction. So the idea of Goldstone theorem is very simple. If you have these broken symmetries, I can use this symmetry to kick the system. When I kick it using this symmetry, then the lattice starts to vibrate. And vibration of the lattice is nothing but a sound wave in a piece of solid object like this one. And this sound wave is a phonon when you quantize it. And this is an example of Nambu-Goldstone boson, which appears when a symmetry is broken. You use the symmetry to kick the system that creates an excitation which is very, very low energy. And you can do the same thing with the other translation too. And if you kick the system using this translation, then you produce this kind of vibration. So this one was a longitudinal photon known, then this one is called transverse phonon. And in either case, energy goes linearly with momenta. So for each broken symmetry, you have two gapless excitations. Both of them have linear dispersion relation. Exactly what Goldstone told us. Same thing happens with superfluid. So in this case, I told you that changing the phase of the wave function is a symmetry, which is spontaneously broken by having chosen one particular position in this potential. And in this case, you have one broken symmetry. And if you look at the excitation spectrum, in this case by neutron scattering on a liquid helium, you see, again, linear relationship between momentum and the energy. And also, if you go to a very, very cold gas of atoms at the level of nanokelvin temperature, they form a Bose-Einstein condensate. Once again, you see this linear relationship between momentum and energy. So it's working again. And this kind of thing is also believed to be happening at the core of exploding star called supernovae. And much of the material in your body actually came from these stars that exploded billions of years ago in a supernova explosion that spread all the elements around into an empty space, and we assembled them together again and formed our body. And at the core of the supernova explosion, there's a remnant called a neutron star, which is a star incredibly dense, as much as atomic nucleus. So one scoop of a neutron star would be like 10 million tons. So incredibly dense. And in this dense core of the neutron star, it is believed that, again, this symmetry of changing the phase of the wave function is broken in a BCS state. So far, it seems to be working everywhere. But now I'm coming back to the first example of magnets on your fridge. So in this case, I told you that spins of the electrons are lined up in some particular way. And there are two possibilities here. One of them is called antiferromagnet, where spins want to be aligned in an anti-parallel direction. Another one is called ferromagnet, where spins want to align in the same direction. And when you take the antiferromagnet, then you do find three-dimensional rotation symmetry. It's now broken to only one axial rotation, because once spins are lined up in this way, you can't rotate the system this way anymore because it's broken. This symmetry is also broken, but this rotation doesn't change the system, so that symmetry is unbroken. So out of three possible symmetries, there's only one left. You have broken two symmetries. So you would expect two gapless degrees of freedom in this system, and lo and behold, you do have them. But in the case of ferromagnet, something is wrong because you have only one such excitation. And if you look at the dispersion relation here, energy is indeed proportional to momentum, seems to work well with the Goldstone's theorem. But for the ferromagnet, it's actually quadratic. Again, something seems to be wrong. So Goldstone proved a theorem, but it's not working in a magnet on your fridge. So what do we do about that? So this is actually very strange, because as I talked about before, when you have this kind of spins lined up, this symmetry of rotation is broken. This symmetry of rotation is broken too. So you can kick the system, and you would imagine that you can create an excitation like this one, and also this one, just like in the case of crystal. But in reality, if you solve the Hamiltonian of the ferromagnet, you'll find only one excitation that actually does this. Neither of these, but somehow a combination of them. So this became a little bit of problem in the literature. First, in the nuclear physics community, where people are trying to understand what exactly is going on at the core of these neutron stars, and start to talk about abnormal number of Nambu-Goldstone bosons. Here's another nuclear physics paper on abnormal number of Nambu-Goldstone bosons. It came back to condensed matter physics, and here they talk about abnormal number of Nambu-Goldstone modes. So it starts to getting realized that, well, we may be missing something here. And even Nambu himself chimed in, and he wrote this paper, Spontaneous Breaking of Lie and Coulter Algebras, in 2003. So in the beginning, he reviews this idea of spontaneous symmetry breaking, how many Goldstone bosons you expect. But then it doesn't work this way, and then talks about, however, there are exceptions to the above theorem. If there are exceptions, that's not really a theorem anymore. So you have to fix that somehow. And I was actually very happy to see this paper because I've known Nambu. He was a very, very humble person. He never bragged about himself. So and he was very, very humble. But in this paper, he actually talked about this, the gapless degrees of freedom as Nambu-Goldstone bosons using his own names. So even though he was a modest person, at least he has some pride in his own works. I was very happy to see that. But nonetheless, anomalous properties is something we wanted to understand. So it turned out that I was giving a course on quantum field theory in Berkeley, and there was a student who was studying condensed matter physics, which is not my field, but he was taking my course. I talked about this example of ferromagnets, and he referred to Goldstone's theorem. Then he raised his hand and said, "Professor, you are wrong." What? Am I wrong? What are you talking about? So we had to actually sit together after the class, and then I soon realized that he knew much more about many of these systems than I did. And I became aware that something I didn't understand. We sat down together and started to understand what's going on. And in the end, we came up with a generalized theorem of Goldstone. So here is how it works. So main difference between antiferromagnet and ferromagnet is how the spins would add up. In the case of antiferromagnet, each spin is antiparallel to each other. So if you sum with the neighboring spins, they cancel. So there is no overall spin of the system. But in ferromagnet, they all add up, so you have actually big spin in the overall system. And what you learn in quantum mechanics class is that spin in z direction can be written as a commutator of spin in x and y directions. And if you see that commutator has a value that reminds you something, it will remind you of canonical commutation relation between x and p. So Sx, which is the kick in this direction, and Sy, which is the kick in that direction, are not independent from each other, but they have a commutator. And when x and p have a commutation relation like this one, x and p together describe 1 degree of freedom, say particle moving in 1 dimension. You need to in classical mechanics, you need to provide initial position and initial velocity to predict what happens afterwards. That's basically x and p. And that's also true in quantum mechanics. You need to specify x and p together to describe 1 degree of freedom. So if you have a similar commutation relation between spin rotation in this way, spin rotation in that way, because of this commutator, you need to use them together to describe 1 degree of freedom, not 2. And that actually turned out to be the crux of the puzzle. So you can formulate this problem in quantum field theory. And when Goldstone proved this theorem, he had a relativity in mind. So he had only this term and that term, but not that one. And if you have this term only, then each of this, what I call the pion field, will be independent from each other. And here you have second power of time derivative, which is in quantum theory energy squared. That's your balance against the spatial derivative squared. In quantum mechanics, that's momentum squared. So energy squared goes together with the momentum squared, and hence linearly proportional to each other. But in the system that doesn't have Lorentz invariance, like a magnet on your fridge, you can have a new term that wasn't there before. And this new term would pair up one of the pion fields and another pion fields so that they are paired. They together describe 1 degree of freedom. And at low energies, this term is linear in E. This is quadratic in E. So this is negligible compared to that one. So energy goes together with momentum squared, and therefore quadratic relation between energy and momentum. And that idea can explain pretty much everything. So when two Nambu-Goldstone boson fields are canonically conjugate to each other, a pair of them describe 1 degree of freedom. And which ones are paired together can be always expressed in terms of these commutators. And the true number of gapless excitations is not the same as the number of broken symmetries, but you need to subtract the half the rank of this commutator matrix, which counts the number of pairs. So out of this many broken symmetries, if you have pairs, you need to subtract 1 for each pair to get the correct number of degrees of freedom. And once you know this formula, you can try this on all the examples known in the literature, and it works every single time. So that's how we managed to understand what's going on. So we were very happy when our paper was accepted in physical review letters. It was even chosen as the editor's suggestion. And we also tried to understand what the underlying mathematics is behind this interesting phenomenon. And this is an obscure form of mathematics most mathematicians don't know about, called the pre-symplectic structure on homogeneous spaces. But once you know the language, then you can use it to describe the universe, just like what Galileo told us. So just this month, I was so honored to receive an award from a Japanese Society Particle Physics Medal for this paper I've written together with the student. So there are many interesting examples. One of them is, again, Bose-Einstein condensate of cold atoms. So in this case, the atom as a whole has a spin. And when you cool down a gas of atom with spin, in this case spin 1, down to nanokelvin temperature, you start with the symmetry of overall three-dimensional rotation of spin, together with the phase of the wave function I mentioned earlier. So you have 4 symmetries to start with. But out of these 4 symmetries, you actually start breaking some of them. So the spin 1 object has 3 possible orientations of spins. So you have actually 3 component field to describe the dynamics of it. But it acquires a particular expectation value, which looks very weird. But if you divide this up into the real part and imaginary part, you can identify that rotating first 2 components and rotating real and imaginary part will keep this combination invariant. So there is 1 unbroken symmetry. So as a result, you have 3 broken symmetries, which is described by some topological space called RP3. But you don't have 3 gapless excitations in the system. Out of 3 symmetries, 1 is standalone and gives you this linear relationship. But the other two form a pair describing, again, only one degree of freedom, not two, and it has this quadratic dispersion relation. So this is the way it works. So I actually begged one of my colleagues in Berkeley, Dan Stamperkern, who was working in the Wolfgang Ketterle's lab at MIT. That was the first place to produce bosons and condensate of cold atoms. So he actually did an experiment to see if this weird relationship really does happen. And it did. It is quadratic. So it works. And if you actually further look into the question of the mathematical origin of it, I don't spend too much time on it, but you can actually formulate the problem in terms of topology of fiber bundles, and you know exactly what's going on here, so that once you understand mathematics, you can even start to classify all possibilities of what pairing is possible for what kind of symmetry and what kind of unbroken symmetry. And now that we understood what's going on, then we can start to use it. The problem at my heart is trying to understand what dark matter of the universe may be. And there's one particular dark matter candidate called axion. And axion is supposed to couple the spins of nucleons, protons and neutrons. And to detect this axion particle, which has never been detected so far, how can we use the spins of neutrons and protons to do an experiment? And I talked about superfluid helium-4 before, where you have 2 protons and 2 neutrons, spins all cancel against each other. But if you have a helium-3, which is made of 2 protons and 1 neutron is not paired, so the spin is still there. And you could actually use this to detect axion. And now that we have understood how the symmetry breaking works, the helium-3 actually has this 9-component wave function, which has the complicated expectation values in the ground state as well. But you know what kind of symmetry breaking is happening. And once again, you have one standalone Goldstone boson, another one based on the pair. So you know exactly what's going on. And using this understanding, we could project how well you might be able to detect the axion that have been produced theoretically by using helium-3 as a detection medium. So that made me much happier. So given that, I started actually use this more and more in many different directions. I did mention dark matter already. Our universe seems to have about 5 times more mass than all the atoms combined. And we still don't know what dark matter is. But without dark matter, we wouldn't have been born, because the dark matter's gravitational pull is what gathered the primordial gas to form them into stars and galaxies. So we were born thanks to dark matter, but we haven't seen it or met it. So I always tell, if I give a public lecture, that I regard dark matter to be my mom, because I was born thanks to her, but I never met her. So we got separated at birth all the way since the Big Bang. So that's the journey I'm still on. I'd like to meet my mom and say thank you. That hasn't happened yet. And if you look at the astronomical observations, there are galaxies called dwarf galaxies, which seem to have rather strange distribution of matter in them. And it doesn't seem to agree with what people predicted theoretically. And the reason why there is a disagreement between theory and experiment is still somewhat controversial in terms of interpretation. But one possibility is to say, well, dark matter distribution is a little flatter than what you would have predicted, because they actually meet each other, scatter themselves, so that it would flatten out towards the center of the galaxy. So that might be the reason why you see this disagreement between observation and experiment. And if you take that idea seriously, you need to come up with a candidate of the theory of dark matter that can scatter among themselves fairly often. So it needs to have a physical size, but should be still light enough to be incorporated into galaxies. And that should remind you, aha, we have seen something like this. Something light, but made of stuff, and has a finite size, and scatters with the other things. That's a pion. Maybe dark matter is also some kind of pion-like Goldstone boson, which is made of dark quarks bound together by dark gluons. And once you take that idea a little seriously, you can work out its property because you now do understand how these Nambu-Goldstone bosons behave. In some cases, you have this topological interaction among the dark pions, which can lead to this 3-to-2 annihilation process. So we call this kind of dark matter strongly interacting massive particle, as opposed to the standard candidate people have been talking about, which is called weakly interacting massive particle. Because this dark pion has a finite size, they can meet and hit each other and change the distribution of matter inside dwarf galaxies. In other cases, you can also rely on another topological property called skyrmion. And skyrmion is a subject that shows up in material science a lot these days because it may be used in spintronics to produce a high-density storage of some sort. But this is actually an idea that emerged originally in particle physics where the pions, which are actually bosons, can describe a fermion called skyrmion. So in that case, you have extra interaction, which can be shown in this diagram, and that can lead to a process called semi-annihilation that had been actually proposed initially by Professor Francesco Di Ramo sitting here with Jesse Taylor. Both of them have been Berkeley postdocs, so I'm very, very proud of them. And so that kind of dark matter candidate is also possible. If that's the case, we better understand the distribution of matter in these dwarf galaxies better. And that's a part of the reason I spent 15 years working with people building instruments for telescopes to do a spectroscopic measurement of multiple objects at the same time. So this is the way you can point telescopes to measure spectra of 2,400 stars at a single time. And that requires a very complicated instrument, which has many, many components in it. But nonetheless, we have actually built this instrument over 15 years of work, which is now in a Subaru telescope. We started observation this year, so we hope to analyze this data very soon. So that's where you might actually see these Goldstone bosons in galaxies. And finally, there's one big puzzle about our universe, why you exist. So when universe started with the Big Bang had a huge amount of energy, and energy can turn into matter. We know that because we can do experiment on it. But when energy turns into matter, it is always accompanied with antimatter. So when photon turns into electron is always accompanied with the antimatter counterpart, positron. So Big Bang had a huge amount of energy that turned into matter and antimatter. And this is always 1-to-1. So Big Bang must have led to the equal amount of matter particles and antimatter particles. But if it stayed that way, eventually universe cools, matter and antimatter meet, they go back to pure energy 1-to-1, so you lose all of them, universe would have been empty and you would not be listening to me today. Something must have happened, namely that somebody picked one antimatter out of a billion and somehow turned into matter so that there's difference between a billion and billion and two. And when they meet, pretty much all of them would annihilate away except that two that remains, and that's you. That's the way universe must have evolved. But the big question here is that who picked up antimatter and turned that into matter? How and when? And again, we don't know the answer to this question. But there's one favorite theory by theorists, especially those people who are having this meeting this week, working on neutrinos. And the idea is that neutrino actually saved us. So here's the idea. So whenever you are talking about a matter particle of electric charge Q, the antimatter particle would have the opposite electric charge minus Q. Because electric charge is always conserved, the Q can never turn into minus Q, so antimatter cannot turn into matter, except when Q is 0, right? Neutrino has no electric charge, charge 0. Antineutrino has charge -0, which is the same as 0. There's only neutrino among the list of all possible matter particles we know in particle physics, which have charge 0, so that in principle could have turned antimatter into matter. So maybe neutrinos actually did that, and that idea was proposed by some of my colleagues, Yanagida and Fukugira. So if that's the case, the neutrinos saved us from the fate of a complete annihilation. So that's yet another superhero we should be thankful to. I have to say, I'm not very good at editing graphics. So out of Incredibles, I had to change I to new for every one of them. It took me a huge amount of time to do so. So I keep using this slide because I spent so much time on it. So that may be a very interesting possibility. Neutrinos might have saved us. But if that's the case, when that happened corresponds to a very early moment of the universe, because the mass of the neutrino that actually caused this process is incredibly high. So that would be a very difficult test, because if you would like to test this theory by creating this very heavy version of neutrino by particle colliders, like OHC, to go up to this kind of energy scale, 10 to 14 GeV. So if I rely on currently available technology, such a machine would be as big as that. And that would require definitely international and possibly interplanetary collaboration. And probably this wouldn't happen in my lifetime. So that would be ultimate future circular collider. So I don't know. But we can hope for something different. So when this heavy particle was produced in the early universe, that might be also due to some kind of new symmetry breaking that leads to a phase transition, just like superconductivity. And when superconductivity happens, I told you already, magnetic flux gets squeezed into tubes. So maybe a phase transition in the early universe that led to this process can also lead to many magnetic tubes, which are called cosmic strings. And energy of the cosmic string network is proportional to its total length. So universe wants to simplify it to reduce the energy by making shorter and shorter. But the process to simplify this network of cosmic strings actually gives you a gravitational wave signal, which turns out to be somewhat large enough to be detected by future missions. Namely, this phase transition in the very earliest moments of the universe that might have reshuffled matter and antimatter could lead to gravitational wave signal, which seems to be scale invariant over many decades of frequencies. If you really see this kind of flat spectrum, that has to be due to something that is scale invariant, cosmic strings being the prime candidate of it. Then we will learn something about earliest moments of the universe, and also at the same time of spontaneous symmetry breaking that will lead to our survival at the end of the day. So what I find really fascinating is that all of these examples I talked about is based on the same equation, and same piece of concept would work in every example on this slide, and that's why I find physics to be a lot of fun. Thank you. Thank you. Wow. I wasn't expecting this. Thank you.
So what a great start for this colloquia season. No pressure on future speakers, but okay. This was the first one. Thank you very much, Hitoshi, for the fantastic talk. And now the floor is open for questions. So there is a question there. Luca.
Historically, who was the first to have the idea of spontaneous symmetry breaking?
It's hard to say. Some people say it's Phil Anderson. Some people think it's Nambu. And then there are other, actually, people who contributed this theorem as well. So, history is always complicated. And especially when you talk about simple theoretical concept, people talk about it. It becomes not clear who actually really initiated that idea. So I don't really know. And certainly I wasn't born back then. So we need to find somebody who is a living witness of that era.
Okay. Next question, especially encouraged from students. Okay, you are not a student.
Students are definitely encouraged.
Thank you for the talk. When you talk about leptogenesis, you mentioned these gravitational wave signatures. What do you think about the test with the light neutrinos in experiments like
So because we
Hypercamioncan?
cannot directly go to that energy scale to build an experiment, that we need to collect many sort of fossils, circumstantial evidence. And doing experiments with light neutrinos and observe its Majorana particle as a CP violation, they are meant to be circumstantial evidence. It's not direct proof, but it's a good circumstantial evidence. And gravitational wave would add another circumstantial evidence. There may be also charged lepton flame violation. That might also be a circumstantial evidence of leptogenesis. So when you can't directly prove it, then you have to start collecting all of these circumstantial evidences. And if they line up to tell you the same story, at some point we probably would believe in that. But we need these evidences first.
Thanks.
Students, don't be shy, don't be shy.
I wrote the paper with the students, so maybe your question would prompt me to write another paper.
When talking about the Higgs bosons, you said that we have the perfect amount of Higgs bosons. Is that number constant? Does it change at all? Like, what does it mean to have an amount of?
Yeah, so it seems to be constant today. It's so rigidly frozen into empty space. So no matter how universe expands, it seems to maintain the same density. But in earlier moments, it was probably less. And if you go to very high temperature, everything would evaporate, and Higgs boson become free particle at some point. And we haven't understood this transition either. Some people think it's actually crossover. There's no phase transition. Some people think it's a first order, like liquid and solid. And so we don't know that yet. That's why people would like to do more experiments to understand the property of the Higgs boson. Excellent question.
Next.
Come on, who wants to write a paper with me?
Exactly. This is your chance.
This one.
Yeah, it's not about the paper, but I'm wondering the final part of your talk where you have these gravitational wave signals from a network of cosmic strings. So can you really unambiguously relate the formation of this string to the origin of right-handed neutrino mass or not?
Yeah, so the idea here is that, there are many theories that does the same thing. So some people speculate that the forces we know are unified into something called ground unified theory. And that kind of ground unified theory tends to have another force, like U1B minus L force, we call that, couples to baryon and lepton numbers. And when the symmetry breaks spontaneously by a phase transition, all of a sudden, one of the neutrino can become as heavy as I mentioned earlier. So that mass comes from the same mechanism that something gets frozen to empty space at a very high temperature, and that would actually give mass to one of these neutrino states. And when those heavy neutrons decay, they don't decay 50-50 into matter and antimatter, maybe 49-51. So that is the idea of leptogenesis. And this phase transition would lead to this network of cosmic strings. So it should be at the similar energy scale as the mass of this heavy neutrino I mentioned earlier. That's why I was talking about 10 to the 14 GeV or something like this. And it's very interesting about gravitational wave that every other experiment I have seen always look at the physics from bottom up. But gravitational wave is looking at physics from top down. So higher the energy scale is, the bigger the signature, so you have a better chance to observe it. So that's why this can be a very, very interesting signature to look for.
Okay, thank you.
Yes, one.
I go.
Yeah, thanks a lot for. So you mentioned again also the previous question, when some of these parameters or let's say values are slightly different, right? The Higgs boson is slightly more far apart. Then it wouldn't have, let's say, life. But this always, to me, sounds okay. It's not life as we know it. So do you think that there might be mathematically or philosophically a universe where the Higgs boson is ever different, and the whole universe looks completely different? Or do you really think that this physics is so exotic and bizarre that for us it's very hard to?
That's a very good question, so we should write a paper together on that one. So I really don't know the answer because we have not understood what exactly the conditions for life to emerge, right? So in principle, once you understand the mechanism, then you can look at all these physical constants to see what combination is required for life to emerge. But we don't know that yet. So even if you change these parameters in some particular way, maybe there's a very narrow corridor where you can keep finding life on its way. I just don't know. So that's a fascinating question we should think about.
Professor, you talked about the cosmic strings in the last few slides.
Right.
And you mentioned the energy per string is proportional to the length of the string.
Right.
And
right.
I have a question. What is exactly the strings? Is it the string same from the string theory strings, or is it just the kind of field solution to the field equation?
It's not the string of string theory, like superstring theory, but it's a string in something you can see in a real piece of superconductor called Abrikosov flux. It's really meant to be magnetic field squeezed into a narrow tube. And that exists, and you can take a picture of it. You can see it move in a film of superconductor. So that's actually much more familiar kind of string to most of us. And so they do exist. And whenever there's a phase transition that breaks the symmetry, it can squeeze the magnetic field in the same way and leads to these cosmic strings.
Okay, thank you very much.
Hello. Hello. You mentioned that we can see pions as Goldstone particles for, if I understood correctly, QCD.
Right.
Why is it that although their mass is quite smaller than the proton and neutron,
right.
Why is it that it's not zero? But
yeah, so that's an excellent question too. So the Goldstone theorem says that whenever there is a symmetry, which is spontaneously broken, you find a massless particle. In the case of QCD, the symmetry we're talking about is called chiral symmetry. But the chiral symmetry is a little broken because the quarks actually have small but finite mass. So it's not exactly symmetric, so this potential is slightly tilted. And if it's tilted, there's really the unique minimum. And around the minimum, potential rises a little bit. So it is still light enough because it rises only a little bit, but it's not zero, so it's not massless because of that. Thank you, because that tells you you've been really paying attention to my talks. I appreciate it. There's another hand up.
So maybe we have time for 2 more questions. Here's one.
Professor, I'm curious if you think that pions are the limit of what makes particles, or if there's something that makes pions themselves. And if you think that we're going to keep discovering more and more small things that make up bigger things, like in a sort of fractal way.
I'm sorry, I didn't understand the question. Can you repeat that for me? Sorry.
You mentioned that what keeps quarks together is pions, no?
Right.
And
No,
I'm
what
curious.
keeps neutrons and protons together is
Yes.
the pion, yeah.
I'm curious if you think that pions, or there is something else that creates pions, that keeps them together, or if you think that there is a limit to what makes matter itself.
I see. Yeah, so when you talk about forces, then you need to have lighter particle to let the force act on longer distance. Heavier particle goes only so much. Lighter particle can further to act a force on something else. In the case of pion, it's light enough that inside the nucleus, neighboring proton can exchange pion to another neutron, and they can attract each other. But if pion were heavier, it goes even the size of the proton itself. It doesn't act on the next particle. That's why you need to have a light pion. And when you ask the question when pion can be produced from some other particles, and that's possible, but those other things are always heavier than pion because the pion is the lightest object that's made of quarks and gluons. Nothing else is lighter than that. So you have to rely on something heavier, which doesn't go very far. So in the end, it doesn't help in keeping the nuclei together. I hope I answered the question.
Okay, we have time for one last question. Then we have to close.
Good afternoon. I was wondering, in the part where you were talking about the neutrinos turning into their own antiparticle, why do we focus on the neutrinos since there are other particles that are their own antiparticles? Why is this?
That's a very good question, too. So in particle physics, we have a theory called the standard model. And we have a specific list of matter particles in the standard model. And if you look at the list, neutrinos are the only matter particles that have charge 0. Everything else has charge 2/3, -1/3, -1. So they cannot possibly go back and forth between matter and antimatter. Neutrino is the only possibility within the matter particle standard model. You can think of some other mechanisms how matter and antimatter might have been reshuffled. But this is pretty much the simplest thing we can think of. So that's why there are a lot of people who are interested in this direction in the community at this moment. And that's why people are doing a lot of experiments with neutrinos these days. Okay? All right.
Okay, so we have to end this colloquium. Unfortunately, I'm so glad to see so many questions, so much interest also for students. So let's thank Hitoshi for the fantastic talk again.
Thank you.
Yeah, no, but we still have to.